The secret is that nobody needs it.
Okay, everyone, welcome back to the afternoon session. I'm very happy to have Luca telling us about nonlinear bosonization, PFT for Fermi liquids and non-Fermi liquids. So, yes.
Thanks a lot for the introduction, and thanks to the long list of organizers, and maybe especially the local ones, for bringing us together. It is a very nice workshop. So I will tell you about our efforts in developing a new effective field theory to describe Fermi liquids, as well as some work in progress on applying it for the strongly interacting cousins of non-Fermi liquids. And so this is work with this sensational team. Each know is a student at Chicago. Umang Mehta recently started a postdoc in University of Boulder, and some of you probably know. So because this is a very diverse audience, I'm going to start nice and slowly and tell you what by telling you what a Fermi liquid is. And the first part of this talk will be all whiteboard, and then maybe we'll take a break, and I'll switch to slides just to be able to say a few more things than would be if it was just whiteboard. So, okay, let's start by what is a Fermi liquid, and why should you care? Oh, and I should write a little bigger. So the simplest way to get a Fermi liquid is just to take a bunch of free fermions. Okay, so let's say you have a box, and you start putting fermions in this box. So if the first fermion you put in, the first electron you put in wants to minimize its energy, it's going to occupy, its wave function will occupy, the longest wave vector state that's allowed. And so to denote the fact that this state is occupied, I'm going to put a little dot here at kx equals 2 pi over L. And now if I add another electron to the box, ignoring spin due to Pauli's exclusion principle, it's going to have to occupy a different state. Okay, so if it wants to keep on minimizing its energy, it will occupy the next smallest wave vector. Okay, and I can keep on doing that. And you see that I'm going to start populating, this plot with more and more points as I add more and more fermions to my box. And I'm going to be interested in the thermodynamic limit, where I send L to infinity, keeping the density of fermions fixed. Okay, so the total number of fermions divided by the volume will be kept fixed. I'll call this the density, let's say, rho. So in this limit, this object here, this mess of fermions, becomes a smooth object, okay, called the Fermi C. and this is the object that I'll talk about. Okay, so there's, and in particular, there's one important dimension for quantity in this game, the Fermi weight vector, which is the size of this Fermi surface, and it's related to density in some simple way. Okay, this is which you can figure out by just counting the number of dots in this thing, and you'll get kf to the d to some number. So this system that we just got from free fermions is, I want to argue, already extremely cool. It's very, it's an extremely gapless system. And it's very different from anything one sees in particle physics, for example, or in kind of more familiar quantum field theories. In particular, it has a whole particle whole continuum of excitations. So what are the low energy excitations of this system? Well, they correspond to taking a fermion just below the Fermi surface somewhere, and placing it somewhere where it can go, right, where there's an unoccupied state just above the Fermi surface. Okay. So this is an excitation that costs essentially zero energy, right? I just did it very close to the Fermi surface, but it lives at a finite wave vector, q. Okay. So there's basically zero energy excitations down to zero wave vector, which is very unusual. And in particular, so if you look at, spectral densities, for example, there's going to be, they're going to look very different. So let's say you look at the spectral density of the density two-point function. I guess it's a bit small. As a function of frequency and wave vector. So this thing is going to fire in this whole region because of these excitations. So you're going to have non-zero imaginary parts to the spectral densities at essentially zero frequency, even at finite momentum, up to some momentum to kf, the largest particle excitation. Okay. And this is very unusual from the perspective of kind of particle physics. Okay, just to contrast this with, let's say, what you would get in a quantum field theory, or let's take the example of CFTs, even the simplest example of just a free scalar. Let's say a free boson. Its two-point function will look something like this. With some I epsilon. So that this object, if you take the imaginary part, it only fires along the light code. Okay. Now we can try to make it more interesting by adding interactions. So for example, if you have an interacting CFT, you'll often get anomalous dimensions. Like this. Okay. And so this does, now we have a whole branch cut with a branch point along the light cone. But the branch cut is over here. Okay. The branch cut is for frequencies larger than q. Another way to see this is to just imagine, perturbatively, you have some scalar that's some particle that can decay into several particles. You start to have a multi-particle continuum. You start to have states for frequencies equal to, let's say I have two momenta, q1 plus q2, which is generically going to be bigger than q1, or can be bigger than q1. Hopefully I got this right. So that you have one-shell states over here, okay? But you never get spectral densities down there. So this is really kind of a signature of this extreme gaplessness of Fermi surfaces. So it's what makes these systems both challenging to study with usual QFT tools, but I think also very interesting. It leads to a lot of new possibilities compared to more traditional quantum field theories. So let me just sketch how you see this particle whole continuum for free fermions.
Hey, Luca, can I ask a question about these pictures? So if you were to do the same thing on the Fermi liquid side as you did for the bosons, turn on some small interaction that doesn't do anything too exciting, what would it look like?
Yes, you're right. So you can also do this. You'll get a multi-particle continuum over here.
Same thing.
So here, even with free fermions, you have this continuum energy here. You can always create multi-particle or multi-particle continuum. the actual analytic structure of the interacting turbine.
So and in momentum space, I thought that you also now can have gapless excitations with larger than 2kF. Is that
With momentum larger than 2kF,
yeah, isn't that
not at zero energy, that costs some energy.
even with interactions?
If it's interacting, if it's sweetly interacting, I wouldn't expect that much to happen. Although, yeah, what do you have in mind? You're saying.
The transfer.
I see. Yeah, no, maybe you're right. Yeah, you're saying some process where you. Yeah, maybe you're right. Maybe it becomes even. Yeah.
Sure. Why is that? It seems like that could be maximum 2 kF. Sorry, I should ask.
No, I'm also not kind of, but I thought. Also, I know that in a large liquid in 1D you get actually that 2kF, 4kF, 6kF. So I think that has to be.
Yeah, I'm completely sure. Let me think about it. So actually, for this talk, I'm mostly going to focus on this part of this drawing, the very low wave vector and energy part. Already here, it's very interesting that we have things below, light or whatever, down to zero. There's also interesting physics happening around here, of course, but I'll mostly focus on both low energy and low wave vector because there's already this. You already see this particle hole continuum, which is pretty non-trivial. So just to sketch how you see it, how you would see it. So you can take here you have free fermions, and you write it like this. With some arbitrary dispersion relation. So here, if you wanted, relativistic fermions would maybe have a linear dispersion relation. Non-relativistic fermions would have something like this. It doesn't really matter. The physics of Fermi liquids doesn't depend too much on what kind of fermions you have. And then you would just look at the two-point function of the density operator.
This is in the ground canonical, not canonical anymore?
It doesn't really matter, but let's do it in the canonical. So I'm turning on a chemical potential.
Okay.
Yeah. So we want to compute the two-point function of this operator. So this is just going to be some fermion loop. Okay, so it's going to involve two fermion propagators. And I won't do the integrals here because I'll show you actually a better way of computing this quantity using bosonization. But if you compute these, where these propagators are given by, and there's an important I epsilon prescription over here. So if you compute this carefully, and it's not too difficult calculation, at low energies, what you find is the following. Okay, so you get, just from this integral, you'll get this branch cut, which has this analyticity that I talked about, and it's all coming from so the imaginary part is all coming from the I epsilon. Okay, so this particle hole continuum is a sign of this extreme gaplessness. Just to mention a few other signs, so this gaplessness has a lot of signatures. It essentially affects any observable you can think of. I'll just mention a few others. So it also affects thermodynamic observables. For example, the specific heat of the system. So specific heat is how your system responds to turning on a temperature, how the energy density increases once you turn on a temperature. And for Fermi liquids, it turns out to be linear in temperature.
Sorry, I'm missing some point here. So,
Yeah.
I mean, you are not turning on interactions yet, are you?
That's right. Here, here for what I'm saying here, I don't even need to turn on interactions. I could, and it wouldn't change much, but
Yeah, but here you mentioned something about branch cuts or something like that.
that's right.
Yeah. So I didn't. So what does this mean actually? This branch cut? that
Well, it's not a single particle.
Uh-huh.
This is a diagram computer, right?
Okay.
There's a loop, but it's right. They're on-shell states. I mean, even if I didn't know finite density, I would also have branch cuts, but they wouldn't correspond to the particle. So Fermi liquids have this type of specific heat at small temperature. Just to contrast it with, for example, CFTs. So for CFT, the energy density, just by scale invariance, has to go like temperature to the spatial dimension plus 1, so that the specific heat goes like T to the D. Okay. And here the dimensions are made up by the Fermi energy or the chemical potential. Okay. So we see that all this is at very low temperature compared to the Fermi energy. We see that at these low temperatures, the specific heat of a Fermi liquid is much larger than that of a CFT. Okay, this is another sign of this extreme gaplessness of Fermi liquids. Another thing I want to mention, because we talked a bit about it in the previous talks, is entanglement. The entanglement entropy of Fermi liquids is very unusual, in that it violates the boundary law, or area law of entanglement. There's an extra log enhancement in the entanglement entropy across some entangling surface. And so this is interesting because it's even larger than the non-universal boundary law, okay, that you have generically. And moreover, the coefficient is completely universal and depends on some geometric properties of the entangling surface and the Fermi surface. So this is something you can, I think, argue can't happen in any relativistic QFT in the vacuum. So the fact that we're not in the vacuum is what's crucial here. Okay, the fact that we're studying finite physics is what allows for this somewhat richer behavior.
Presumably L has to be larger than the scale set by the density, no? For this.
Yes. Otherwise there would just be one fermion. In fact, this kf appears here. This is a dimensionless quantity. So I said this number is universal, it involves kf. Okay, so this is all cool, but we understand free fermions pretty well, so I'll talk about interactive fermions.
So if the Fermi surface is not isotropic, in that expression, what is kf?
Yeah, so okay. There's a universal geometric expression for this, which involves an integral along the Fermi surface and an integral along the entangling surface. It's called the Widom formula. Maybe I'll write it in case you want to look it up. For an isotropic Fermi surface, it looks like this, but there's a generalization, which is a very really elegant formula that only involves really the geometry of the Fermi surface and the entangling surface.
Presumably Widom wasn't computing entanglement.
Right, so I never really understood why it's called I never understood. I mean, I tried reading the paper from Widom, but
how far in the past is Widom? 19th century or what?
No, Critical Exponents Guide pre-Canada.
okay, yeah. So I'm not exactly sure what's
Your D is spatial dimension.
my D is spatial dimension. Yeah.
So is this Widom formula tested numerically?
Yes, so that's a good question. There are some tests of it, although we heard about subtleties in getting entanglement entropy from the lattice. In particular, there are some claims. So one question is how, whether this formula might be more general than for Fermi liquids. So for free Fermi gas, you can prove it. For Fermi liquids, there are some arguments, and it seems fairly convincing that this should still be true for interacting Fermi liquids. Then there's a question of whether it applies even more generally, maybe to classic phase of non-Fermi liquids. And so there has been some numerical work on trying to study lattice systems that are expected to be in a non-Fermi liquid phase. And they claim, I think there was a paper claiming that there was a factor of 2.
I think that paper is wrong.
Yeah, I think that. Okay, good. So I think the numerics is difficult, but but I think there's some, yeah, there definitely exists tests of this formula, at least for interaction.
So the prefactor only depends on the shape of the Fermi surface.
Yeah, I mean, maybe I can write it down. So this thing really is integral over the Fermi surface, then integral over the boundary of your, let's say, of A. You trace out A, so that your entangling surface. Okay, I probably shouldn't have tried to do this slide, but and roughly, so there's a unit vector for okay, so you have an entangling surface, and there's a unit vector for the entangling surface pointing away, and same with the Fermi surface. Okay, they live in different spaces, of course. So and you compute something like this. And I think that's basically it. You get powers of, yeah, so this will give you L to the e minus 1, this will give you roughly kf to the e minus 1. And then, there's some universal number in front, but this is basically the formula. And I think everything else is about. So it was guessed from free fermions by, wired constructions, where you try to take free fermions and make them do complicated enough things that you can guess the general structure, but there isn't a really nice, elegant proof for Fermi liquids. That would be nice to have, and maybe it's even valid beyond that. So. Any other questions? Okay, so of course we understand free fermions fairly well. The reason people are interested in Fermi liquids is that they also describe interacting fermions. And in particular, a lot of the motivation for our work is to go beyond even Fermi liquids and understand strongly interacting phases of matter that still have some notion of a Fermi surface but have really kind of non-trivial critical exponents. So a non-Fermi liquid is to a Fermi liquid, but a non-trivial, but an interacting CFT is to a free CFT. And there are several reasons to want to go beyond Fermi liquid theory and study non-Fermi liquids. In fact, there's, I think, two reasons, two motivations that are basically independent. The first is experimental, namely the fact that there's now a growing number of systems that seem to show behavior, so seem to have Fermi surfaces. We know that they have Fermi surfaces, but they show behavior that's just inconsistent with Fermi liquid phenomenology. We don't understand why, the thermodynamic properties, the linear response is just very different from what you'd expect in Fermi liquids. And a class of these materials go under the name of strange metals. And moreover, I should say the fact that the behavior, which is strange and not Fermi liquid-like, is fairly universal across many systems, suggests that there might be a universal answer. So that's one motivation, and a completely independent motivation, I think, is just from theory, which is, why would you go beyond Fermi liquids? Well, just because you can. More precisely, we know that there are relevant deformations of Fermi liquids that drive them to something else. Okay. So if you think of a Fermi liquid as your kind of UV fixed point, we know that they have relevant deformations, which will trigger RG flow to something that has to be different. Okay. And in some cases, the expectation or the hope is that it describes a non-Fermi liquid.
So relevant deformations?
Yes.
If you add other stuff.
Yeah, if you add other stuff. And this relevant deformation usually, well, typically what it looks like is coupling the Fermi liquid to a gapless boson. A gapless boson, which could either be an order parameter that you tunes to criticality, or a gauge field. Those are both deformations which, you can just study them around the Fermi liquid fixed point, which we understand fairly well, and we know they're relevant. So we know that you lose perturbative control there. We don't necessarily know what happens, but we know that something happens.
Is there a finite number of relevant operators?
Well, it depends on the symmetries you want to put in. Let's say, rotation invariance. Then I think yes. In fact, I would say 2, probably. So the critical order parameter. If you also have to tell me something about the symmetry of the order parameter. And if you say that, I think that nails it down to one relevant definition.
Is it the usual superconducting instability, but now addressed with?
No, so it's something else. It's relevant. It's not marginally relevant. It's relevant. So that's also why that's also the hope that it's. So of course the kind of ultimate fate of a lot of these systems is the superconducting or superfluid instability, right? And even Fermi liquids, without adding extra degrees of freedom, we don't have BCS instability, which will drag you to a superconducting phase. This is something else, and the hope is that this leads you to a different phase of matter that maybe then is unstable to superconductivity, but that's not the main kind of driving force. Okay. So there do exist some perturbative approaches to studying this problem. And in fact, there's some experts in the group. But I think it's fair to say, without offending these experts, that these aren't as clean as, for example, the Wilson-Fisher fixed points and other approaches we have for CFTs, for interacting CFTs. In fact, they all have some kind of dirty secret, or often not even a secret. A famous approach is explicitly non-local. This is originally due to angle check. There are also large N approaches, which are very interesting, but they often have many subtleties. In particular, in many cases, the large N limit doesn't commute with the IR limit, so that it's unclear whether your 1 over N corrections are controlled, or it's unclear if you take N to infinity first. It's unclear if you're learning about a true fixed point that exists at finite but very large N.
But isn't this something that one always has to worry about for any large N?
For any large N?
Yes.
Like for S, like
I think it's something you should always worry about, but it's not something that's always a problem. So, for example, the ON critical exponents we can get pretty well in a 1 over N expansion. Here, I think we basically can't. And, yeah.
By the way, regarding this non-locality, some of the non-Fermi liquids will arise in non-local systems.
Yes, but I don't want to add any unnecessary ingredients.
Is this non-locality secretly just some gauge field?
Somewhat?
Some gauge field
No.
that you've
No.
figured it out?
No, it's bad. It's you couple the boson that's tuned to being gapless has a kinetic term that looks like this: 1 plus epsilon. Oh boy, I guess you can see this. And this is your control parameter.
It's not local because they need that to get control, not because.
Yeah, when epsilon is 0, which is very non-local, it's marginal. The interaction becomes marginal.
What is it? You did try to say gapless boson. What was gapless boson? What is interaction?
Yukawa.
And what's the motivation to consider this interaction?
What's the motivation?
Yes.
It's the only relevant interaction.
What's the physical situation where that's a change?
I mean, any non-fine-tuned situation will have this interaction. So if your question is why is there a gapless boson?
Yeah.
Yeah. So okay, there depends a bit on situation. So in the case of strange metals, the expectation that maybe one possibility is that there's an order parameter that's close to criticality. This could be so often people invoke the Ising nematic order parameter. So there's a transition where a C4 symmetry is broken down to Z2, and then this is the gapless boson that your Fermi liquid couples to. In some other phases of matter, you might hope that maybe there's just a gapless boson there, an emergent gauge field. And if it's there, then you can have this type of physics.
You could probably also just couple to a gauge field, right?
Yeah, that's another. But it has to be there, right? It's not. has to be, and this is 2 + 1, the kind of most interesting situation where the interaction is really relevant. So it can't just be the photon. Yes?
So here you set it up as something arising from coupling a Fermi liquid to something else.
Yeah.
So is that the most promising direction to try to understand non-Fermi liquids, or just one of many possible ways to get it?
So there are many definitions of non-Fermi liquids. I would say this is a good definition of non-Fermi liquid. A strongly interacting fixed point obtained from Fermi liquid. Because one other definition of non-Fermi liquids is anything that's not a Fermi liquid, and that's not a good definition. Okay. So this is a little more specific. And what I'm insisting on is the fact that it's strongly interacting but still has a Fermi surface. Okay, in particular, CFT is not a non-Fermi liquid. It's just a different.
But why can the definition not be something with a Fermi surface but it's not a Fermi liquid?
Yeah, so maybe you could. Yeah. And you're saying maybe you can get there without even starting from a Fermi liquid. Yeah, no. So yeah, I'm open to. Yeah. I think this is one way to be sure you'll get the physics you want. Okay. And there's another method. They all have dirty secrets. As I was saying, there's some that also break the symmetries you care about. So there's a number of methods, and we know some things about these fixed points, but there's certainly room for improvement. So the point of this talk, yeah, and what my kind of view on this is that we don't have much control on the non-Fermi liquid fixed points because we don't have a good starting point to access them. And what I mean by a starting point is a good effective field theory for Fermi liquids. So that's kind of what motivated our work to build a good effective field theory for Fermi liquids. Now you may be familiar with an existing effective field theory for Fermi liquids, and I'll briefly talk about it too, so that everyone's on the same page, due to Polchinski and Shankar. Which I think is beautiful work from the 90s. And one thing that it showed is it kind of put Landau's intuition from many years back on the kind of rigorous framework, more rigorous framework of Wilsonian RG, and explained why Fermi liquids are stable or fairly stable against interactions, and why there's only a special class of interactions that Landau had identified called Landau parameters that you should kind of care about, and everything else you can, roughly speaking, throw away. And so the way they did this is really just use the framework of effective field theory. Okay? So the same way you would, let's say you have a regular kind of QFT, and you want to know what terms are. So let me just take an example of a relativistic QFT, and you want to know whether some interaction is relevant or not. You would just use the scaling of your Gaussian fixed point to figure this out. Okay? So like here you would say phi has dimension d minus 2 over 2. So that this operator here times let me maybe focus on let's say d equals 4. Okay, so that this is how you figure out that this theory in 4 dimensions has phi 4 is marginal at tree level. If n is smaller than 4, it's relevant, meaning it grows, and if it's larger, it's irrelevant. So if all your couplings are irrelevant, you have a controlled effective field theory. Okay, effective field theories usually have an infinite power of irrelevant interactions. And if you have one, even just one relevant interaction, this typically means that you're going to lose perturbative control at low energies. Okay, because this interaction is going to give larger and larger corrections. So let's do this for Fermi liquids. And the way they set this up is to write down the most, so I'll start here, is to to write down, to start with the theory of free fermions and write down the most general quartic interaction for these fermions. Okay, so something like this. So here I'm going to let the coupling depend on wave vectors on these momenta of the fermions. Usually one just expands for small wave vectors, right? But here, as we saw, low energy physics doesn't take you to zero wave vector, so we have to be a little more careful. Okay. So our fermions have some kind of dispersion relation, mechanical potential, so that the low energy physics is at some finite wave vector. Okay. And let's be in 2 plus 1 dimension just for concreteness, but you can do this in any dimension. Good. So our low energy physics is happening close to this Fermi surface, right? So let me zoom in on a point of the Fermi surface, and let's write the direction normal to the Fermi surface, let's denote it by Kn, and the directions parallel to it by K parallel. So here, if we, to understand if this interaction is relevant or irrelevant, we're going to scale the tree level action to be equal to 1. S0 is scale like 1. So let's see how it scales. So there's so the time derivative cancels the dt. And good. And I forgot to say one thing. So as we scale to low energies, Kn goes to 0. But K parallel just stays finite, right? Because K parallel is taking us along kind of massless the soft direction. Okay, so K parallel doesn't scale. So this thing, how it, so and you know, in general dimensions, you'll have d minus 1 K parallels in just one direction normal to the Fermi surface. This will go like K normal psi squared. So we learned that psi scales like 1 over square root of K normal. Okay. So now let's look at the interaction. Oh, and I should also say frequency scales like K normal. Okay, this you can see by just expanding this around the Fermi surface. It'll have some linear expansion that looks like this. The coefficient of the linear term is called the Fermi velocity. Okay, so this is how you should scale things. And now let's see if this interaction is relevant or irrelevant. So there's one t. Let's evaluate the delta function to kill one of the momentum integrals. So we have 3 momentum integrals, which will each give a k normal. And then we have 4 fermions. So this will, so if the momentum, if all the fermions are scaling to the Fermi surface, if they're all really soft modes, we'll go like 1 over Kn, Kn cubed times Kn squared, which scales like 1. Okay, so we see that there are marginal interactions. So there's one assumption I made here, which is that all the fermions, all these wave vectors K can scale to the Fermi surface together. And this actually doesn't generally happen. So if they're not scaling to the Fermi surface together, then psi K won't be a soft mode, right? It's not going to scale in this way. So there's going to be some hard, very high energy mode, and then this interaction would instead be irrelevant. So we have to check that indeed they're scaling to the Fermi surface together. All these wave vectors. let's say K1, so K1 without loss of generality, I'll just put along the x-axis like this. I'm taking it to scale to the Fermi surface, but this, yeah.
It's a 1 over k squared, isn't it? 1 over that, not a k squared.
Sorry, say again.
I think there's just a typo. I just want to make sure I understand though. Is it?
Oh, yes.
1 over k squared.
Yeah. Yeah, so, right, so let's see if all the momenta are indeed can be scaled to the Fermi surface. So let's send K1 to point in this direction. K2 is going to point in some arbitrary direction, okay, and go to the Fermi surface. K3 will point in some other arbitrary direction. Okay, and K4, because the momentum conservation has to sum to, so K3 plus K4 has to sum to this. Let me use another color. And so we see that generically it's not going to, this is K4. So it's not at all on the Fermi surface, okay? So actually, most interactions aren't marginal. There's only special vectors which satisfy the fact that they're all going to the Fermi surface together. And how do I get that? Well, I have to set K3 to be equal to either K1 or K2. Okay. So for example, I can set K3 to be equal to K1, and then K4 can just be equal to K2. That satisfies momentum conservation. They're all scaling to the Fermi surface together. Okay. Or I can just flip this.
Equal to minus.
Yeah, I mean their dagger is good. And so we see that out of this big, infinite set of couplings, there's only a much smaller set of them that matters, which is when we're in this configuration. So we can label them by these two vectors, K1 and K2. Okay. And in fact, because we're scaling things to the Fermi surface, we can label them just with their angle. Say theta 1 and theta 2. And moreover, if you have rotation invariance, it's actually just going to depend on the difference between angles.
There is another possibility, which is this.
Yes.
Like if there are exactly
Don't spoil.
antipodal.
Yes, there's another possibility. Let me just take a little bit of time on this possibility first. So these couplings, so it's a subset of this infinite class of couplings, and these are called Banach vectors. Okay, sometimes they're expanded in harmonics this way for a circular Fermi surface. And these FLs, F0, F1, F2 are called Banach vectors. Okay. So you can think of these as Wilsonian coefficients of the effective field theory. They correspond to marginal interactions. In fact, it turns out, so usually when you have marginal interactions, you start looking at quantum corrections. And it turns out that these corrections are exactly marginal, which is very unusual from the perspective of let's say, particle physics QFT, at least without supersymmetry. And we'll see a better way to, you have this quartic term in this language that has an exactly marginal interaction. We'll see that there's a better description of it. That makes sense. Yes.
But all orders means one loop here now.
Well, there's some diagrams that are. Maybe you're saying that there's a class of diagrams that don't.
I don't remember. I thought it was enough to show that it's marginal at one loop to understand it's exactly marginal.
Yeah, because there's.
Because it's a non-relativistic fermions.
Exactly.
You cannot
So there's
move backwards.
Right. So there's a class of diagrams where you only have two particle hole cuts, and those are the ones you check for the fact that it's marginal. Yeah. But in the description I'll give, it's going to be obvious why it's marginal. Okay. And as Zohar hinted, there's actually one other possibility, right? Instead of setting K3 to be equal to K1, I could set K2 to be related to K1. In fact, K2 equals to minus K1. Okay. In this case, they sum to 0. So K3 can be anything, and then K4 will be minus K3. And this is what's called the BCS interaction, which was famously missed by Landau, but it's also there. And in fact, it turns out to be marginally relevant. Well, it can be marginally relevant. But it's also labeled by two angles.
labeled by two angles?
So maybe let me. There are only two vectors.
Oh,
Yeah,
it's only a function of one angle.
Yeah, rotation invariance. Good. Okay, yeah. So I think that's what I want to say on the board. So we could either take a break now already,
How do
or
you
I
avoid
try to
double?
transition. Yes, sir.
How do you avoid double counting? I was always confused. Maybe you can.
No, so okay, yeah.
Because in the special case of f at 180 degrees is the same as this.
Yes. So there's a limit of the Landau parameters that have to be equal to the BCS interactions. Yeah. There's a kind of redundancy in the degrees of freedom that can be a bit annoying. Yes, I don't have a very good answer for it, but it's correct. Yeah. So just so that everyone understands, in the limit where there's obviously a solution where both things hold, right? K1 is minus K2, and K3 is also equal. Let's say probably this, right? Where you could have interpreted it, and you could have interpreted this both as a Landau interaction or as a BCS interaction. And what this tells you is that in this limit of kind of head-on forward scattering, so Landau parameters describe forward scattering, right? Because the outgoing vectors are the same as the ingoing vectors, right? So you have two particles that just kind of keep on, they interact, but they keep on going. Whereas BCS is head-on scattering. But if you have head-on forward scattering, that's both a BCS interaction and a Landau interaction. So this tells you that in that limit, both of these vertices are the same. So there's a kind of redundancy in these Wilsonian coefficients.
How's that consistent with the fact that one is exactly marginal, the other one is marginally relevant?
Good, okay. Yes, good question.
Maybe some of the harmonics are
So I think all the harmonics of this guy flow.
Essentially, this small angle scattering doesn't dominate, just some very small.
Yeah, exactly.
It's
Usually
for magnitude. For at least for these leading contributions to Fermi liquid theory. The subleading contributions, like corrections of order t squared to specific heat, they're actually very important. But it's kind of a different kinematic regime.
So maybe it's the same thing that Max said, but what usually happens is that there's one harmonic of the BCS interaction that grows, which is kind of decoupled from the small angle, which would tell you about that all harmonics are growing the same rate. Yeah.
So back to the argument about non-local term, that was kind of bad from Naya and Lucia, but this is also non-local interaction.
Okay, so this interaction is non-local in momentum, which isn't necessarily bad, right? In fact, if you could expand this as a polynomial in the wave vectors, you'd be perfectly happy, right? However, it's true that the way I set this up, it's not obvious whether it will correspond to local action, once you focus on the right degrees of freedom. But yeah, so okay, so there's maybe I should say before the break, that why do we need a new effective field theory? So there's several drawbacks of this effective field theory. One is that RG is a bit subtle, right? You have to work a little harder because low energy means scaling momentum to the Fermi surface, and things are formulated in momentum space, which is not very usual in quantum field theory. So that's to your point. There's another drawback, which is that if you actually start doing perturbative calculations with this action, what you'll see is that there's a number of cancellations in loops, or approximate cancellations in fermion loops, which make kind of scaling analysis very difficult because it's hard to guess even how a given correlation function will scale with external momentum. And so this kind of approximate cancellation in loops is one of the problems that bosonization can solve. That this new effective field theory kind of makes manifest. So this is what the state of the field has been kind of for since the 90s. We have these effective field theories, and a lot of these perturbative constructions are kind of based on versions of this effective field theory. And our hope is to kind of build a bosonized description of this system that avoids some of these problems, and that's better suited for both perturbative and maybe non-perturbative calculations. Any other questions before the break?
doesn't apply in situations when you have some singular points on the Fermi surface.
Yes.
So is your bosonized theory supposed to work there?
Yeah, so it's not going to be much better there, but so usually when you have singular points on the Fermi surface, so, you know, yeah, let's say your dispersion relation, okay, I will, so when you have a lattice, you often have situations with a dispersion relation, let me write kx and dy, the Brillouin zone, where the Fermi surface is not you know, rotationally symmetric, and in particular there's often situations where you have Van Hook singularities. And what's happening here is that you basically have a kind of regular fermion over here, right? The Dirac type fermion there. So you have extra degrees of freedom that are there, and there. Yeah, what we'll see in the effective field theory that I'll show, the cutoff or the strong coupling scale of the effective field theory will be the curvature of the Fermi surface. So it's not going to solve this problem. And you know, you might ask whether you can improve by adding the. We kind of know what's happening, right? It's not a crazy degree of freedom that's entering the game. So there might be a way to. It'd be interesting if there's a way to introduce this degree of freedom and recover a EFT with a finite cutoff. I'm not sure about.
So 10-minute break?
Yeah.
What do you think? Does that sound good? Okay.
Yeah.
Cool. Okay. We reconvene in 10 minutes. So.
to the bosonic description. But this advantage becomes much more dramatic when you look at more complicated observables. So let's say you want to study the connected 14-point function of density in this theory. Okay? And even though it's a theory of free fermions, it's not an easy diagram to compute. You have to compute this fermion loop with 14 insertions and then symmetrize over these insertions. So there are many actual diagrams that I didn't show. Whereas on the bosonic side, it's immediately obvious that any connected higher point function of densities vanish because we have a Gaussian theory and the density is linear in the Gaussian field. Okay, so there's just no vortex, right? And in fact, if you compute this carefully, this fermion loop carefully, you'll see that after symmetrizing over external vertices and after computing at least one of the integrals, you'll find that it indeed vanishes. Okay? So it's not an easy thing to see on the Fermion side.
There's no slick argument on the Fermion side.
Isn't that the axial anomaly?
The axial anomaly?
Well, sorry, the null anomaly. The conservation of the axial current doesn't tell you that.
So you're saying higher point functions will be constrained? So that will probably fix the 2-point function?
Naively, both the vector and the axial currents are constrained.
Yeah, yeah.
That naively makes all diagrams vanish. And then there's one exception, which is the row one that you wrote. Because of the anomaly.
Yeah. No, maybe you're right. Maybe there is that argument. Yeah, I think that might be right. So that might be a nice argument. Yeah. Good. But I guess it wasn't known in the 70s. Yeah, I think that might be true. I mean, you need Lorentz invariance, but here, yeah, okay, that's fine. Okay, but so at least perturbatively, without invoking anomalies, there's a kind of advantage to this bosonic description, and this really carries over once we study more complicated systems. Yeah.
Sorry, on the left-hand side, do you mean the connected?
Connected, yes.
But it is trivial because this is a free theory connected part. Of course, it will.
Of the it's fermion bilinear.
Sorry.
It's a fermion bilinear, right? So it doesn't. I mean, it's not. Yeah, it's not trivial. So for example, in higher dimensions, it's not zero.
Okay.
It's not any connected correlation of fermions will be zero.
But this is a free theory.
Yes.
Okay. Okay. Yeah. It's sorry.
So this simplification of the bosonic description carries over. This kind of perturbative simplification carries over when you study more complicated theories. So let's, for example, couple our theory to a gapless boson, which is what we'll be interested in doing in higher dimensions. And then we study this theory, the Schwinger model, or 1 + 1 = 3D. So from the fermion side, it looks like a pretty non-trivial theory. I mean, okay, I'm sure there are ways to solve this trivially, but perturbatively, it looks like a pretty hard problem. There's a relevant interaction. This has mass dimension 1, and so if you're used to higher dimensions, you would expect that this is impossible to solve. But on the boson side, it's immediately it's kind of already solved. This is how the photon couples to the boson. The entire theory is Gaussian. We can solve it live, go to unitary gauge. We see that there's a mass equal to the charge.
I think the coupling should be like an axiom, huh?
Yeah, so maybe I told Einstein. Let me not answer that. Good. So right. So we immediately see that it's a gap. So it's a gap photon. So life is not as simple as 1 + 1D Dirac fermions. Okay. And in fact, these cancellations, as I mentioned, don't happen generically. They don't happen in higher dimension. In fact, they don't even happen if you have more complicated dispersion relations and non-relativistic fermions. But it turns out that there's still a remnant of these cancellations in higher dimensions and more generally in the form of approximate loop cancellations. So these are even worse because you have these fermion loops, and you try to guess how it's going to scale, and there's some amount of cancellation happening, but there's still a finite answer post-cancellation. So these make perturbative analyses of non-Fermi liquids quite difficult. On the other hand, so the bosonized description that I'll talk about makes all of this completely transparent. So in particular, the fact that we had no connected higher point functions of density before came from the fact that there were no interactions in the bosonized description. So now the small remainders post-cancellation of these fermion loops will come from small irrelevant couplings, irrelevant interactions in the bosonized description. So we now will have vertices generically, and they will be small, will be irrelevant under scaling, and so you'll know, in particular, this will make scaling completely transparent. You'll know how these hierarchical functions scale. So generally speaking, there's going to be two sources of nonlinearities. As I mentioned before, if you have something more complicated than a relativistic dispersion relation, even in 1 plus 1D, and this was known in 1 plus 1D, you do have interactions on the boson side. These cancellations don't happen. So something like this still carries over to higher dimension. There are these types of nonlinearities. But there's another source of nonlinearity which is much more inevitable and kind of universal, and simply comes from the geometry of the Fermi surface. In particular, the curvature of the Fermi surface will lead to interactions, to vertices in the bosonized description that are just fixed by, really just by the geometry of the Fermi surface. Okay. So let's see how we actually get this this action. So our effective filter is actually going to be much closer to Landau's description of Fermi liquids than Shankar-Kolchinsky. So let me just briefly tell you how this goes. So this is the system we're interested in. As I mentioned, it's a very gapless system. And one way to think of the large gaplessness of Fermi surfaces is as kind of wobbles of the Fermi surface, right? So these particle hole excitations where I take particles here and put them there, if I do a lot of them, I'm going to change the shape of the Fermi surface. Okay, you can think of this as kind of carrying the gaplessness of the system. So as I mentioned before, there's an important dimensionful quantity in this problem, the Fermi wave vector, which begs the question of whether there's an effective description for this system at distances long compared to 1 over kf. And indeed there is. So if you imagine you have a Fermi liquid in this room, you can separate this room into a bunch of boxes, each of which are still much bigger than 1 over kf. Okay? And since they're all much bigger than 1 over kf, you can still define a smooth Fermi surface. Okay, we're kind of still in the thermodynamic limit for each of these boxes. And so now we have a kind of Fermi surface that depends both on momentum space like before, but also on real space. Okay. So this is really inherently a semi-classical description, but it's controlled by this large kf. Okay, we're kind of doing an expansion in low energy physics in units of, or low momentum physics in units of kf. So now our Fermi surface can depend on space. For example, you could have more fermions of momentum to the right over here, more fermions of momentum to the left over here. And so, if I take this picture and time evolve it, inevitably what's going to happen is that they're going to flow towards the middle, and we'll have a little more density over here. Okay. So there's some kind of continuity relation that describes this system, which is just the collisionless Boltzmann equation, okay, describing the kind of conservation of probability, if you want, or of occupation in the space.
I'm going to try and answer the question, but I'm not quite sure how to phrase it. I'm always nervous when there's x and p's in the same quantum equation.
Yes.
Heisenberg tells us we
yes.
can't. So there's certainly some fermion states in the Fermi surface whose wave functions spread over the entire box, but they're the very low energy ones that live in the middle of the blobs.
Yes.
And you're not accessing them.
I would say very high energy. So exciting them would cost, putting a hole there would cost a huge amount of energy.
Yeah, so they're the one.
So the very
that's why
ones,
it's okay to break things up locally.
Exactly.
Things that are spread everywhere are just not in the game.
Exactly.
Okay.
Yes. Yeah. So there are quantum states, but they're very high energy. Good. So this is basically, so this is just for free fermions. This collisionless kinetic equation, right? This is just kind of describing particles going past each other, doing nothing. Well, as a warm-up, let's just try to find an action that will produce this equation as its equation in motion. Okay, so this will be the kind of first task that we'll set ourselves to have. So the degree of freedom will be this occupation number f, okay, which tells you whether a state in my box at position x and with momentum p is occupied or not. Okay. So so this is our degree of freedom. It's not just an arbitrary function of x and p. Okay, it's going to be a kind of subclass of functions that's equal to 1 or 0, 1 if the state is occupied and 0 otherwise. So we're really talking about sharp Fermi surfaces. And the goal is to write down an effective action for this degree of freedom, directly for the shape of the Fermi surface.
Is the area fixed?
The total area, so total charge, but locally, integral over p of this is the density, which can be any, which is not defined by rings, but in higher dimensions. But the density, the local density can be any place. Okay, let's look. but the integral over x and p of this object is the total charge, which is
Is this the sense in which this is the bosonization just because it's the action for the density?
Yeah. This is a bosonic object. You can kind of think of it as a fermion bilinear. Actually, yeah, there is a precise sense in which you can think of it as a fermion bilinear. But yeah, this is a bosonic object.
You're only writing px and py just for pictures, or is it important that
it's not important.
Later, will you explain how to write down the single fermion operator?
No. No, so that's a very good question. So, you know, bosonizing, I had all this spiel about why it's useful, and I gave examples where I was talking about bosonic operators. So, of course, bosonization is a good idea if you want to study bosonic correlation functions. It's probably not a good idea if you want to study fermionic correlation functions. And in fact, yeah, so I think in 1 + 1, of course, you know, there we understand everything. We know how to study single fermion, realize a single fermion operator. But here, I don't think there's a simple answer to that. And I think there are good reasons for there just not to be.
But even there, it's kind of stupid to study. It's complicated.
Yeah, no, exactly. It's not.
Even there, you don't want to study in
Yes.
bosonic language.
Yeah. So here the goal is just to have a bosonic theory that reproduces the bosonic, you know, any bosonic correlation function of Fermi liquids. So this is our degree of freedom, and you know, in this free fermion warm-up, we already know what the goal is. We have to figure out an action whose equation of motion will be the collisionless Boltzmann equation. Okay, here I generalize just a little bit to add a potential that depends on x, so that there's an extra force term in the collision in the Boltzmann equation. Okay, this is just the collisionless Boltzmann equation. So let's think a little more.
One question about this. So, that is this supposed to be valid for arbitrary potential, or for only for essentially slowly varying potential? Just for the some sense Boltzmann equation is semi-classical.
Yes, yeah, I think slowly varying. Slowly varying will be enough for that. Slower than 1 over PF.
Very naive question. If you're going to be trying to write down an effective action for the shape, could you try to think of it as some kind of number Goto-like thing, something like by a constraint that the volume is fixed?
Yeah, kind of, except momentum space and space aren't really the same thing. So, you know, Goto is, okay, the action of a brain, but here it's a brain that lives in momentum space and real space, and just the physics of these things, you know, it's not a metric space, are just different. So, I think, you know, maybe more yes, but not, I don't think that will take you very far. Okay, so we want to look, so this is the equation of motion we want to reproduce. Let's think a little more about what where our degree of freedom is living. So as I mentioned, it's our degree of freedom isn't an arbitrary function of x and p. So let's think a little more about what kind of subset of functions it is. And to think about this, let's imagine starting with some kind of reference state. Okay, so here I'm considering a Fermi surface at rest, so it doesn't depend on x. It's the same everywhere, and it's just isotropic, okay, rotation invariance. And let's think about what possible states f of x and p we can reach under some kind of arbitrary Hamiltonian evolution, starting from this state. So the equation of motion that we have for f, I can write it in this way. That makes it look like a bit like a Schrödinger equation, where here this commutator is the Poisson bracket of these two functions. Okay, these are both functions of x and t, and this is what this commutator is. So this equation, this time evolution equation, we can formally solve by just exponentiating the Poisson bracket, the commutator. So this is what the solution will look like as a function of our initial states. So we see that the states we can access correspond to the basically the orbits of our initial state, of our seed state, under some group. Okay. And this group is this group G is the group whose algebra are Poisson brackets. So this group turns out to be the group of canonical transformations. Okay, canonical transformations are generated by functions of x and t, and their algebra are just Poisson brackets. So our degree of freedom is living kind of in the orbits, so it's called a coadjoint orbit because this f you can think of as living in the adjoint, or the coadjoint. Right? It also depends on x and p. And it's kind of our manifold of degrees of freedom, of low-energy degrees of freedom, are in the coadjoint orbit of this seed state under the group G. So just to give you a much simpler example of this, this is essentially the same as ferromagnets. ferromagnets have an order parameter in the adjoint, right? So that the Goldstone manifold is the Goldstone manifold is basically the action of SU2 on this order parameter, okay, which is the sphere. Okay, so this is the coadjoint orbit of, let's say, of this order parameter under the. This tells you what the low energy is here.
What's adjoint about it? The order parameters and the fundamental.
No, for SO2, so sorry.
SO3.
SO3, yeah, SO3.
And what is the difference between adjoint and co-adjoint?
I'm not the right person to ask.
But it's co-adjoint. I remember
it's
the title of your
It has to
paper.
be co-adjoint. I'm sure someone here knows if they want to speak.
So, sorry, is energy just the one parameter group, or?
No, this is, so here I'm kind of, I kind of made up a general Hamiltonian, and this is really just the entire group.
So you allow for arbitrary Hamiltonian?
I allow for arbitrary Hamiltonians just to kind of figure out where my degree of freedom lives. Okay, and I don't want to study the physics of that Hamiltonian, but just to understand that.
It's the space of canonical transformations on X and P. Is that the degrees of freedom?
X and P in whatever dimension you're in.
Okay.
So this equation is just the Liouville equation, right?
Yes.
Basically, you're interpreting the distribution function of the Liouville equation as an actual degree of freedom.
Yes. Yeah, not the whole distribution. It's a sub.
Do that, like whenever
No. Yeah. Well, I mean, maybe. So, but you won't always get a nice effective field theory for it. So, so this equation is also used in the context of just weakly interacting particles without Fermi surfaces, right? But there, it's just not a good degree. There isn't going to be a nice effective field theory for it. So here, what's crucial is that it's it's kind of expanded around this. Okay, so our degree of freedom is we can represent it in this way with F, or equivalently as the group element that rotated us from some reference state to F. Okay, or to make an analogy with kind of Goldstone physics, you could write it as a parenthesis with an element of the algebra phi. So here phi will be an element of the algebra, so it's a function of X and P. Okay, vector X and vector P, general dimensions. Not every phi is independent. So two phis that differ by a rotation that commutes with the seed state, that leaves the reference state invariant, lead to the same state F. Okay, so they're equivalent. So really our degree of freedom lives in a quotient space, which is the group of canonical transformations mod the stabilizer of this seed state.
The stabilizer are just functions of momentum?
The stabilizer?
Yeah.
Not quite, because so it depends on your seed state.
The seed state you said was only a function of momentum.
Yeah, so functions of momentum are in the stabilizer, but it's even a little bigger.
Oh, okay.
Because they have to, basically you get, so grad P of this gives you a delta function on the Fermi surface. So grad X of your function has to vanish on the Fermi surface. Elsewhere it can be non-zero. So it's a function of momentum is fine, but it's actually much bigger. Yeah, maybe let me write this. What is the stabilizer H? So alpha in the, let's say the algebra, will satisfy alpha commutator F0, and let's put this Fermi surface rest. So this will be grad X alpha grad P of this, which is going to be delta function on the Fermi surface, a vector, unit vector, okay, something like this. Or n hat is unit vector pointing away from the Fermi surface. This is the condition for an element of the algebra to be in the stabilizer. So basically, it can actually be a function of x, but its derivative with respect to x has to vanish on the Fermi surface. And so it turns out that you can use this kind of redundancy. You can choose an alpha to reduce the degrees of freedom as usual. So here, the analogous statement here would be SU2 mod the stabilizer of the vector in the adjoint, or SO3. So that you can, your degree of freedom isn't a general element of the SU2 algebra, but rather just living on the sphere. Here's the way you can reduce the degree of freedom using this alpha in such a way that phi no longer depends on this vector momentum, but only on, so you reduce one argument of phi, so that it only depends on the angle around the Fermi surface. You can always find an alpha that such that phi has this form. So this is starting to look maybe a little like what you might expect the degree of freedom of a Fermi liquid to be. Okay, it's a scalar field. We have a scalar field at every point of the Fermi surface, which you can kind of think of as a particle hole pair. Okay, so now we need to write down, in an EFT mindset, the most general action for this degree of freedom, for f or phi or equivalent. So we'll write down all terms, that we can, and essentially most terms, will be easy to guess. There's just one term that's going to be very special, which is a Wessel-Witten term. It has this form, and what's special about it is that, so written in this way, it looks like it makes reference to the seed state, or equivalently to the group element that rotates my arbitrary reference state into my real state. Which seems like it shouldn't, but this is just, if you look at the equations of motion you get from this action, it only depends on that. So this is a Wessel-Witten term that exists for any, quotient space of this form where you have a group mod to the stabilizer of the adjoints, and it even has an and for SU2, it's a very famous term, which is what gives the Z equals 2 dispersion of ferromagnets. Okay, it's something that looks roughly like plus nonlinear.
Why is this integrated over T only?
Say again.
Why is it integrated over T only?
Yeah, so it's so the trace here. So this is the kind of general form this thing takes for an arbitrary group. Here, this is going to be a trace over the.
X and P.
Yeah, so it's going to be an integral over X and P.
And is the coefficient is a special topological number in front or
yes.
No? Yes.
So, okay, for compact groups, definitely.
Yeah.
Here, it's a bit less obvious. Yeah, I don't have a good argument for why it should be quantized. For most, if you look at for most observables that you get out of this action, the normalization doesn't really enter. So I don't know if there are many consequences to what it's equal to, but yeah, then I'm not.
But this is not. It's not defined on some extension in the bulk. Like
you can write it this way. Yes, you can write it in a way TDS, in a way that only makes
reference
to F. Yeah.
What does it trace again?
Yes, the trace means integral x p. It's the sum over elements of the
Point
algebra.
is that U inverse dt U is an element of the Lie algebra.
Yes.
So you can think of it as a function.
Yes.
It's not important for you that this coefficient has a particular value, or any value will work?
I think so. For what I'll be saying, though, but more generally, I think it's a good question, and I'm not sure what the answer is.
Zero is okay.
No.
Then how could it not matter dramatically?
Well,
does it just cancel on everything else?
So you can rescale it away in many. That's maybe just an obvious statement. Like the quadratic level obviously won't matter.
Then why do you need it?
Why do you need it?
Yeah.
No. You can rescale it away the same way that you can canonically normalize an action, but you better not be zero. But I think that's an interesting question where we're thinking about it, but I don't have a very good answer.
But if you want to match the free fermions,
yes. Yes. So okay. Good. So if you wanted to match the free fermions, let me just say that this is the other term you would add. Okay, let me postpone this by 20 seconds. So this is a special term. Every other term will be very intuitive. Basically, we'll write down any term that can involve this f. The simplest possible term is just linear in this f. Okay, that looks like this. We'll add more general terms later. But it turns out that this action with these two terms, if you compute the equation of motion, you get the collisionless Boltzmann equation. Okay, so this is a theory. We've succeeded in describing a free Fermi gas. And and so you were asking. So obviously, if I change this coefficient here, it will no longer match a free Fermi gas. but I can change this coefficient here, and it will again match. So there's a kind of at least for that question, it doesn't really matter what the coefficient is here if you can give it, if you interpret this not as the energy, the dispersion relation of the fermions, but as something else. Yes.
So say the form of not doesn't matter.
Yes, exactly. There's a kind of background independence of kind of like for pions.
So you can choose any F not Li.
Correct. Except for conserved things, so the total charge has to be the one you want. The cojoint orbit doesn't depend on what point of the orbit you chose to.
Another question. So I assume that X and P are all non-complex variables, or does it apply also to Fermi surface, say metals, or you have a finite limit?
So it's actually better. Okay, when X and P are compact, there's a kind of argument for quantization of this term. I'm not confident enough about it to say it, but there's one of these. Basically, yeah. So if X and P are compact, your Fermi surface is a discrete object, really. Okay, so there's a discretization, which tells you that actually the canonical transformations, right? The smallest P translation is by 2 pi over L, and imposing that this is a symmetry, and turning on some winding of phi, which will be like the kind of lodestone. You can. It looks like you can kind of prove quantization. So it's actually even nicer if you have compact space.
Usually we think about P being compact, not X. So I mean, typically we like to say, well, X just is equal.
Oh, you're saying you have a lattice. Okay, no, sorry.
No, I meant like, yeah.
Yeah, I was talking about putting the theory on a torus. But yeah, I think that's fine. I mean, obviously, I want not too much. I mean, probably formally you'd have to start working with discrete transformations of X and P.
Does it affect any of this issue of quantization of this condition?
I think it can help. It can help if you have a lattice, either in momentum space or in position space. It can help for quantization. But I'm still not super happy with the argument, but it looks like it can help.
But the scale of quantization of P could be a much larger variable than where the Fermi surface sits, in which case you're not in the regime of validity of your theory anyway. So by the time you realize P is compact, you're way out.
Right. That's right. Yeah, the lattice, indeed, if the lattice constant is much smaller than PF, I'm not going to talk about it. Yeah, no, I think the more promising route to quantization is just studying it on finite volume, on a torus. There, P is discrete, and saying something about invariance under that transformation. Because that's a canonical transformation that doesn't vanish at infinity, right? You're really kind of shifting.
I have I think 2 questions are probably just identical in their answer. So one is, what are you expanding in from the putting in these equations? And the second is, how do you know that you should write E of P plus V of X instead of something much more complicated?
Yes.
With all sorts of P's and X's.
Yes, good. So here I'm not really expanding yet, and I haven't written the most general thing yet, right? So this is kind of a little bit of a fine-tuned situation. Maybe let me So the point of EFT is that not just to reproduce free fermions, is that now we have a framework where we can add arbitrary terms, right? So what we're going to do now is just write down the most general functional of X. That's going to be local in space, because the usual assumption of effective field theory that we haven't forgotten massless degrees of freedom, and but an arbitrary, and we'll write this in a gradient expansion.
But you're not focusing on the Fermi surface itself yet. You're just describing a free Fermi gas in some convoluted way.
This action describes a free Fermi gas. This action describes Fermi liquid theory. Okay. So here this was a kind of fine-tuned situation where I showed 2 terms, and those are the ones that reproduce free Fermi gas. But now we know how to write down the most general thing. We'll just write down most general functional of F, local in space, but there's no reason for it to be local in this P label. Okay. And as usual, there's going to be a gradient expansion, so I didn't write down everything, okay, but there's also higher gradient terms, and so on. Yeah, there was a question.
So the object that you wrote on the previous slide, this is an exact description of
free Fermi gas? Yes. Yeah.
And you can prove that?
Oh, sorry, the equation of motion is exactly the collisionless kinetic equation. Let me say it this way.
So it's not exactly Fermi gas.
Great, yeah. So it's equivalent to this equation.
But if I start calculating density density correlation functions.
Yes.
I mean, does it
Yes.
exactly
Yeah. Yeah.
some
Yes.
endpoint function?
Yes. Yeah.
So it's exactly, so it's an exact, or what's not exact about it? Or just to
So when we'll compute things, we'll have to expand. So I think this formulation is exact, but when we'll compute correlation functions, we're going to actually expand around some reference states. And it's going to be difficult, meaning there's going to be an infinite tower. So once you expand in fluctuations, you'll have an infinite tower of irrelevant corrections, which contribute to these higher point functions. And it's exact in the EFT sense, right? You can get better and better precision by including more of them, and we'll be able to do this. And what's crazy is that, so, even for free fermions, this interacting boson theory will be an easier way to get endpoint functions of densities of the free Fermi gas. Okay, and in the boson description, it's much easier for the interacting Fermi. Yeah, in this sense, it's exact. And okay, so this is what higher order terms will look like. There's going to be higher gradient corrections and so on. This leading term turns out to precisely describe Landau parameters. Okay? It depends on two momenta. Low energies, they're going to be close to the Fermi surface anyways, and one can show that this this reproduces kind of Landau's theory for liquids. But we see that there's an infinite generalization of Landau parameters that correspond to these more and more relevant corrections to Fermi liquids. These are all Wilsonian coefficients of this effective field theory. They're measurable. They'll have some value in helium-3 or whatever Fermi liquid you want to study.
You don't have the BCS coupling conspicuously.
Right. So that's this is work in progress. This we're not completely sure yet how to incorporate.
So you cannot yet reproduce all those bosonic stuff.
Yes. There's BCS, and another interesting thing that we can't reproduce is 2KF physics. I mean, so we have some ideas, but they're not as minimalist as what I'm showing here.
You mean like Friedel oscillations?
Yes, because there's low energy physics even at very large momentum, and here I think at small momentum we can kind of do that's not an issue, but so we're not reproducing all of the low energy. Yes, but we have this is working. Okay, so let me show you some examples for how to use it. So in most applications, I'm basically going to expand things. So this is kind of fully nonlinear theory, but I'm going to expand things similar to how you would do this with Goldstones in this file. So I'm going to be evaluating this thing here. So whenever we're expanding, we're actually going to choose a reference state, let's say a spherical Fermi surface, and we want to study the physics around this spherical Fermi surface. So I think probably in all the applications I'll talk about now, I'm going to take F0 to be this rotation invariant Fermi surface, and F you can just obtain by expanding, right? This expression using the commutation relations. Reading order, you'll have things like this. And this quantity here will be, so F0 just depends on P. But really it depends on the norm of P, so this will again be this n hat vector localized at the Fermi surface. Okay, and there's going to be higher order terms that you can get using this algebra. So here I'm just using the Poisson reference. And you see that once you expand, the physics is all localized on the Fermi surface. Okay, you'll have a bunch of delta functions so that all these P integrals are going to be localized on the Fermi surface, and you'll be left with theta integrals over this soft direction. And phi, just to remind you, phi is a function of x and theta. So if you do this just to quadratic order, this is the action you get. Here, I'm going to first expand just the free fermion part. We'll talk later about the other terms. This is the action you get to quadratic order. So we have, and I'm focusing on 2 + 1 dimensions. We also have an integral over this kind of flavor index theta. Okay? And what we have is basically something that looks like a chiral boson. Okay, 1 + 1d, this would be the action for a relativistic chiral boson. At every point of the Fermi surface. And it just goes away. It's the dispersion relation, it has a velocity. It goes away from the Fermi surface. Good. And each of these chiral bosons are decoupled, okay, in this Gaussian action.
So was phi an arbitrary function of x and p to start with?
Which we reduce to x and theta.
Right. The values of phi of p that are not on the Fermi surface, do they have 0 action or infinite action?
They don't, how to say, like it's kind of like asking, what about the boson boson in the direction away from the sphere?
I see.
There's just
I see. They're just not, okay. Right. Thank you.
Should we think of it as gapped out or just infiniteness?
As an effective field theorist, same thing. Yeah. Okay, so this is the quadratic action. This action was actually guessed many years ago by these people who were trying to, who knew about bosonization 1 + 1d and were trying to guess something for higher dimensions. But they didn't know how to go beyond this to nonlinear working. But already with this Gaussian action, we can do a bunch of things. So we can compute again this density 2-point function. So density, like in the 1D case, is linear in the bosonic field. But now there's this integral over flavors. Okay, this is what the total density looks like. And this you can get from f, right? The rho is the integral over p of f. This is what you expand. So the density 2-point function, again, instead of being a Fermi loop, is now just a tree-level thing. But it's a bit more subtle than just a tree-level diagram because there's this integral over flavors. Okay? And this is how you're going to get. So this is the integral you get. This is just the scalar propagator from this action. And this integral is very easy to compute. You get this. So you get this particle continuum, the branch cut. And this integral was crucial to get this non-ellipticity, right? So we have a tree-level diagram that gave us a non-ellipticity. This is not very usual. The point is that there's a lot of degrees of freedom that we're using. So one way to think of this data is as a flavor index, but maybe a kind of a little more realistic way is that this integral in the fermionic description is an integral over frequency and momentum. Right? You can separate momentum into radial momentum and angle. And in a sense, what we've done, so in the fermion loop, we have something like this, right? Yeah. So in a sense, what our effective field theory has done is that it's already computed or kind of integrated out these integrals over kind of hard modes, over frequency and weight vectors, and left for evaluation the integrals over the soft theta variable that's running over the Fermi surface. So this is why it's a kind of shortcut to a lot of computations because it's already automatically computed these things.
And theta is computed, and theta is some very non-local function of phi, basically. N of theta.
No, sorry. N of theta is the unit vector pointing away from the Fermi surface. It's cosine theta, sine theta.
So it's a very non-local function of phi, or it's just like sine theta, cosine theta?
Yeah, it's cosine theta, sine theta. It just depends on.
But if the Fermi surface is curved, you have to first compute phi, find the shape, and then extract the normal. So it's a very non-local function of phi.
Of theta. So let's imagine we have a reference state that's a crazy Fermi surface.
Yes.
Then it's going to be, given by some curve, and n of theta will depend. So let's use theta to parameterize this curve. It's no longer an angle, but just and then n of theta will depend in order.
N of theta is computed from the reference state.
From the reference states.
Because the corrected Fermi surface includes phi.
Exactly. And
so
because I've linearized.
So you don't include the corrections to the shape.
I do, but those are cubic terms. I'm linearizing.
Okay.
Yeah. So indeed, phi is changing the shape of the Fermi surface, but actually I'm linearizing. So really, you can all write everything as depending on f0 on the original Fermi surface and have arbitrary orders in phi.
So can you think about higher terms of just resumming them? That basically the shape has changed and therefore n has changed.
Yes. I think quite explicitly, right? Just by the way, so if you read it this way, it's exactly what this is doing. It's yeah. Although there are nonlinear terms coming not just from the expansion of there are terms that were nonlinear in F already. So there's a bit of mixing of these two.
So in your actions, Luca, you have some symmetries that you fix theta, you can check the some functions that that varies only depends on the directions of functions.
Yeah.
Do you take that as an AC?
So this is kind of an accident of this Gaussian theory, as we'll see. Yeah. Indeed. Yeah. So this theory has like any Gaussian theory, it has many symmetries. And most of them will go over. Yeah, in fact, let's go. Let's see. Let's go to what's next? Oh yeah, I just wanted to talk about these lambda parameters. So here, the next term we can look at is this, and if you expand this in phi, this is what the full action looks like. And so this is the only term I had forgotten that also contributes to the Gaussian action. Everything else is going to be cubic in phi. So this is the kind of Gaussian approximation to the full theory, and it involves just these chiral bosons that are now coupled by Landau parameters. Okay, and here it's immediately obvious why these Landau parameters are exactly marginal. They're just part of the Gaussian action. Okay, there's no calculation to do that.
So if I seriously take the analogy with 2D bosonization,
yeah,
I would say that the BCS parameters are cosine phi minus phi.
Yes. Yeah.
But that doesn't work.
I don't know how to make sense of this. In fact, I don't know how to make. It's not a fermionic object. So people have done. There exists words in the literature saying you do that and you add something that makes it fermionic.
No, I'm just saying I cosine phi minus phi prime.
For the BCS interaction, you mean? Yes. So no. Yeah.
That's what you do in 2D.
That's right. That's right. Yeah. I think that's not the right way to do it. So I think let's see if I can give a good argument.
Also in 2D, one parameter is exactly marginal. That's the Latinger liquid parameter, and the other parameter is the BKT parameter.
Yeah.
Which is marginally relevant.
Right.
So it seems like a very perfect analogy.
Yes. Yeah. So no, and we definitely tried to push this analogy, but there just isn't. I mean, phi. There's no simple reason for phi to be compact here, and we have a different way of kind of incorporating BCS in this approach, which actually involves different additional degrees of freedom, and I think it kind of has to. Maybe I can elaborate offline. Yeah.
So under U1 symmetry, phi just shifts by constant.
Yes.
So an object like e to the I phi has charge 1. So it should create the overlap with one fermion or one particle state.
Yes, but the way I formulated it, there's not a good reason for phi to be compact. That's what I'm worried about.
Oh, it does not connect.
Right. So
that doesn't seem right. It shifts under U1.
Yeah. Yeah, so the question is how U1 is embedded in canonical transformations. Naively, if what you're saying is correct, it's basically a constant canonical transformation. The canonical transformation that doesn't have any dependence on X and P.
But it does shift phi.
But it does shift phi, yeah.
But
right.
It's consistent unless phi is compact.
Right, yeah. Okay, I mean, we can discuss later. I can tell you what, I would want this cosine phi business to be the right answer because it would be very simple. But
it's like there's no way out. Like phi has to be compact.
Mm-hmm.
And e to the I phi should be an operator which creates something with charge 1. And therefore should be permanent. Yeah.
So that's this if U1 indeed is embedded as a constant shift, as a constant.
But it is.
Yeah, maybe. I can tell you, so all your arguments are very good. I have a much more pedestrian problem, which is it just doesn't work. I mean, you look at you can look at correlation functions of this cosine phi operator. It's completely wrong. I mean, it doesn't behave. So there's definitely something that's being missed. So you could say before adding it to the action, right? You could say, well, let me check what the 2-point function of psi dagger psi is, right? Cosine 2 phi, cosine minus 2 phi, and it's not. It doesn't work out. So maybe there's some dumb mistake.
You can simply just look at e to the I, like the psi dagger psi. Yeah. What is the 2-point function?
No, psi dagger psi. That's fine. Those are neutral. That's basically the density. So any neutral operator is
psi
fine.
dagger is 1 point, psi is another.
So yeah, that's even worse. I mean, that's fermionic. Yeah. I was giving an example that's not fermionic but charged. I'm saying those are maybe simpler but still not obvious. And these are all.
So relatedly, do you know how to couple external gauge fields to the charge?
Yes.
Okay, that seems like it's a long way towards answering.
Yes.
These?
Yeah.
Yeah.
Yes.
Okay. But you don't know how. Okay.
Yeah. Yeah. No, you're just pointing out that I don't have a good answer to because it does seem like, yeah, no, I'm not sure. Okay, so now let's look at nonlinear terms, right? That's the point of this approach, that we can go beyond this. So just to kind of illustrate.
One more question, Ken?
Yeah.
One more stupid analogy.
Okay, yeah.
So if I just look at the first term,
yeah,
it looks like what we call sometimes Florianian or
yes,
the cave
exactly.
model.
Right.
Does this have any significance?
Yes, yes. I mean, it's a chiral boson that's relativistic. And, yeah. In 1 plus 1D, this is a theory of two chiral bosons that have, yeah, so it's exactly that.
Of course, it has to be the same.
Yeah. So let me show you, the next terms in this expansion. So there's nonlinear terms, they're cubic terms. There's some that are really universal and just come from this Westerby-Witten term and involve no new, Wilsonian coefficient that I didn't already tell you about. And in particular, note that they're quite interesting because they're coupling different angles, different patches. Okay, there's derivatives with respect to theta, and they're kind of proportional to the curvature of the Fermi surface. Okay, they're proportional to this how this n hat vector. I mean, here this is just for a spherical Fermi surface, but I wrote it this way to kind of make clear that the geometry is coming in. And then there's some less universal cubic terms, which are, in the case of free Fermi gas, will just come from these, the dispersion relation. So this is similar to what happens in 1 plus 1 meters, something like the curvature of the dispersion relation, which leads to cubic terms. And so what you can check is that if you go back to the Goodwill action and see how things scale, you'll find that these cubic terms are all irrelevant, okay, and the higher order terms are even more relevant. So we really have a kind of well-controlled effective field theory. Of course, we haven't included BCS, but all these interactions are irrelevant. They're going to give small corrections to observables. However, they're irrelevant, but they're breaking a lot of symmetries, right? Because we had a Gaussian action. So they're going to give, for some observables, like nonlinear response, they're going to give the leading correction. And in fact, so with this cubic action, you can compute the density 3-point function, for example. And this is something that would have been 0 in this previous theory, right? So this is an object that's known not to be 0, so there's clearly something missing in these older papers, and this is what gives the missing readings. So not only is it I mentioned that let me go back a little bit. So these interactions are irrelevant, and this is what explains why these fermion loops are not as big as you would have thought, just from kind of naive dimensional analysis, because they involve an irrelevant vertex in the bosonic description. Here, for the 3-point function, you just have one insertion of this irrelevant vertex. For higher point functions, there's going to be more, and it's completely obvious to guess how things scale. You just count how many penalties of irrelevant vertices you have to use to make something non-zero. So scaling is obvious, and actually computing these things concretely, is also easier in this side. It's just evaluating these tree level diagrams.
And what is this formula on the bottom?
So here, this is how a density endpoint function scales with frequency. This is not very good. I should have written omega to the 0. So, okay, I didn't go over the argument, but you might, if you just looked at the expression for this loop in the fermionic description and looked at how many powers of omega and q there are, you would have guessed something much larger. You would have guessed 1 over omega to the n minus 2, something like this. So for the 2-point function, there's actually no cancellation. The guess is correct. And for an n-point function, there are n minus 2 cancellations.
What about the q scheme?
What about?
The q behavior says it's for omega also.
Yeah, so this is a regime where omega scales like q. I'm saying the general kind of scaling behavior as omega scales like q.
And this is not like a linear regime with the external momenta.
Right, yes. Yeah, so it's omega scales like q and not. Right. When you have several densities, there's other regimes that so it's the kind of most generic and omega going like q regime.
So that matches the requirement?
Yes, so actually the hard part of this check is the side. So there's a 70-page paper from 10 years ago that we were trying to match it to. In the regime, so actually we check that for away from where you have the discontinuity for omega larger than q, and there you can show it matches. Omega larger than q. All omega is larger than VFQ. Just so that you're away. It's a little easier to do the check because you're away from the non-lattice.
What if it's just set omega to 0?
Yeah, no. So okay, there are many simpler checks you can do, and they all work. Yes.
The people who wrote the 70-page free field theory calculation avoid mistakes. It sounds hard.
Avoiding mistakes?
Well, I mean, you have some way of doing it which is really quick and easy.
Right, right.
If somebody had to do a 70-page long
Right.
free field theory calculation, they may or may not have gotten it right. So.
Yeah. Yes. Yeah. No.
But it's Metzner and
No, absolutely. It's before, but they say.
But you end up matching without correcting.
Yes. Yeah.
You mentioned the free Fermi gas?
This one is free Fermi, yeah. So for them, it's impossible.
Free Fermi gas.
Free Fermi gas. For them, it's impossible to not do free Fermi gas, right? But for us, it would be easy to just include lined out parameters here. You have one more vertex. So we can, of course, push this stuff, but for them, there we won't have anything to match against. Okay, so let's. Yes, am I running out of time?
You had many questions, maybe like 10-ish
Okay,
minutes? Does that work?
Yeah, that should be enough. So because people care about anomalies here, and I will mention a connection to a work that partially motivated some of what we did, which was this paper where they proposed that that Fermi liquids can be thought of as systems that have a big emergent symmetry. Roughly speaking, a number conservation at every point of the Fermi surface. Okay, and from the perspective of this Gaussian action that we had, it seems like a pretty natural thing, right? All these patches are decoupled, so it seems like a pretty reasonable thing to say. So there's this big emergent symmetry, and moreover, it has an anomaly. So okay, it has an anomaly which looks like the 3 + 1D chiral anomaly. And in particular, and one more ingredient is that, so part of the gauge field, so since it's an emergent symmetry, you can't control what the gauge field is equal to in the IR. And part of the gauge field gets activated against your will, the theta depends, and that's how it knows about the Fermi surface. So the global and theta part of the symmetry is just the regular U1 symmetry that you have microscopically, but everything else is symmetries. And you can check that this, if you plug this in here, it has exactly the right form such that if you turn on a real electric field here, you'll start depleting fermions over here and bring them on the right. Okay, so this big U1, many U1 symmetries are broken in a very precise way. That's described by this. So I think this is a very nice idea because it hopes to bring non-perturbative tools in the difficult problem of Fermi liquids and maybe non-Fermi liquids. But there's some issues with this. So there are some that are kind of immediately apparent from this equation. The first that you might worry a little bit about is that it's partially in momentum space and partially in space. Okay? And okay, again, the structure of these of phase space is very different than the structure of space. And maybe more pragmatically, the thing appearing on the right-hand side, this Kf, is dynamical, right? It's the same thing as the density. So density at a point theta is how many, how big a lump you have at that point of the Fermi surface. And that's exactly, if you have a big lump, you're changing Kf, right? So really what this looks like is the linearization of something around Fermi surface at rest. Okay? And on the right-hand side, we have more of an operator rather than just a pure background engagement. So in our way of seeing it, this equation is really just a, and one last thing I should say, well no, let me not say that. So in our way of seeing it, this equation is really a linearization of just a covariant conservation equation in phase space. So basically the Liouville equation in phase space, which looks like this. And if you take this equation and linearize it so that this current knows about the shape of the Fermi surface, the leading order, you'll get something that looks like this curve.
What is the space of labels in this equation? I?
Here I runs over x and p.
X
so it's not mu, but yeah.
Not t.
And t, sorry, and t, yeah. So there's one more than but of course, yeah, it's mostly going to involve tx and theta. Right, so basically what I'm saying here is that Fermi liquids themselves have more structure than just this equation. So you might say, well, but this anomaly is it's still what's emerging at very low energies if you linearize. But the point is that it's emerging only in the limit where the theory is Gaussian, right? Where it has probably a lot of other symmetries. So what I'm saying is that the nonlinear theory, the full description of Fermi liquids, including these nonlinear terms, still has structure as kind of rigid as the equation they proposed, but it has this form. Okay, good. So let me talk a little bit about going beyond Fermi liquids, maybe just 5 minutes, and then I'll wrap up. So the point of all of this is not just to describe Fermi liquids that already have kind of pretty good descriptions for. The hope is to go beyond. And in particular, we want to take this system and study these RG flows towards new non-perturbative or perturbative fixed points that still have a Fermi surface, so still have this extreme gaplessness, but have kind of non-trivial critical exponents. And the way this is usually done, as we discussed before, is to take your Fermi liquid and couple it to a gapless boson, okay, which I'll take to be just a scalar, tunes to criticality, so there's no mass term. And here this is Yukawa coupling written in bosonic language, right? This is my density. So this is kind of the leading, the linearized description of this problem. So what's interesting is that there is a linearized description of this problem, right? In the Fermion language, the coupling is a Yukawa interaction, which is an interaction. Here, even though this isn't the full action, but it's already non-trivial at the Gaussian level. So we can already solve the Gaussian level to kind of see what happens. Let's look at the external scalar two-point function. So because it couples to density, it's going to feel this density two-point function that has this particle hole continuum, sometimes called Landau damping. And at small frequencies, which is the regime that where things are interesting in this space, so frequencies smaller than q, this is what it looks like. And so you see that there's this kind of emergent scaling behavior, z equals 3 scaling behavior, where omega wants to scale like q. So this is often what's taken as the starting point in the fermionic approaches. In fermionic approaches, what people often do is resum a class of diagrams, put things back in the action, and say, okay, this is the thing we start with, and then we'll do perturbative expansions from this kind of z equals 3 UV fixed point. Here, what's nice is that it's kind of a more honest thing to do in the sense that it is the Gaussian action. So our Gaussian action has the starting point is this z equals 3 theory, and we're going to perturb away from it. And good. So now you have to add the nonlinearities, and the bad news is that they're relevant, or the good news is that they're relevant, so that you at least in d equals 2, which means that you lose perturbative control. So what changed from the Fermi liquid we had before is that now I'm scaling things differently, right? We're studying this scaling regime, or omega scales like q cubed, and in this regime, the nonlinear terms. So interestingly, the nonlinear terms that are relevant are the Western means, the ones that are universal. These turn out to be irrelevant. So we have this infinite tower of interactions that are relevant.
Like dangerously irrelevant.
That are relevant.
They're dangerously irrelevant.
So in the omega, it goes like q cube scaling. They're
in the UV fixed point, they're irrelevant, and the infrared they become relevant.
Yeah, maybe you can say it this way. Let me say just the thing I'm saying is around this fixed point, yes. They're relevant.
Yes.
Yeah.
They're relevant or they're marginal?
They're relevant in d equals 2. The critical dimension is 3 plus 1. So matching with known things from Fermi approach. So they're relevant. So just if you don't do anything else, you completely lose perturbative control. But now you can try to build a perturbative approach. So in particular, you can recycle every approach that already existed in the Fermion language, including the ones I trashed earlier. Maybe looking at coupling it to a non-local boson. So if you take this theory at epsilon equals 0, they're marginal. And interestingly, you can also do other approaches, which I think are very hard to do in the Fermion approach. So you can do a 3 minus or a 4 minus epsilon expansion, because you can kind of do things analytically in deep in this approach. Whereas, well, I don't know if this has been attempted, maybe actually as Max or someone else, but in the Fermionic approach. And so this is what we're doing. It's not a trivial calculation either, but the hope is that it's still advantageous because you have a few loops in advance of the Fermionic approach, right? So the first loop diagram looks like this. So here I have, let's say I'm looking at the phi two-point function. It couples to my little phi through these cubic vertices. What this is emulating on the Fermion side is this 3-loop diagram. Because you've kind of certainly saved a little bit of time. Okay, so I think probably I'll stop here and take questions if there are any.
Questions?
So on your slide with the anomaly, yeah, you had the phase-based conservation law, and then I'm assuming you're linearizing like this Poisson bracket type.
Yes, exactly.
So the higher order corrections, do they depend only on A, or do they depend on J and the
They
dynamic?
depend on, roughly speaking, it's kind of what you'd expect. So you plug KF here, you view KF, KF is related to J, right? It's J to some funny power, but and then you kind of expand J around the background KF. Roughly, it's just this.
Okay, so the violation of the current conservation is only dependent on the background.
Meaning it goes away. It's like a covariant.
If big A goes to 0.
Yeah, it's like a covariant conservation equation.
Okay.
Other questions?
Yeah.
Oh, sorry.
So what is kind of the symmetry that fixes the Weissman-Witten term?
So the Weissman-Witten term has a huge symmetry. It's invariant under all canonical transformations.
Why is that symmetry to look at?
It's not a symmetry. So every other term in the action breaks all of the symmetries.
So why
is it there? I mean, it has no reason not to be there. Or what is the question?
No, I mean it's a very constrained term, right? This Weissman-Witten.
That's right. Yeah.
Right. So the correlations between various coefficients, various terms in that term was very
Exactly. Yeah, that's what. Yeah.
So,
exactly.
so what is the deep? Usually we use symmetry to constrain.
Okay, yeah. So if you were trying to guess this Weissman term perturbatively, order by order, yeah, it has invariance under any canonical transformations.
And why is that important?
For what? It's the only such term in the action.
But why should I look for terms with data invariant under canonical transformations?
You should look for. Okay, I think I see what you're saying. You're saying that in terms of f, I allowed for any term, right? Yeah. Okay. The point is that this term looks like it doesn't depend on f. So I kind of cheated, right? And I have to fix this cheat, right? I wrote it in terms of this f naught and u, and I have to somehow make up for the fact that I cheated and didn't use the actual degree of freedom, right? And that's what's very constraining. It has a very rigid nonlinear structure. Only for a very specific choice will it lead to an equation of motion back in the f variable that only involves f.
Is there a proof?
A proof of
this physics term?
Yes, it depends on the group, yeah, I guess it's a question of what I2 of some group is, and you're asking whether it can be bigger.
What's by 2?
Or H2. H2.
Which words?
No, so it's kind of it's like a one-dimensional Weissman-Witten term, right? Similar to the ferromagnets. Even though ferromagnets are in higher dimensions, the Weissman term is kind of.
It just comes from the Kirillov 2 form.
Yeah, exactly. It's always a 2 form.
So in the Cairo-Lagrangian, like a pedestrian reason why we should have a Weissman term is to break some symmetries we don't want.
Yes.
Is there some way to phrase it that way here?
Right. So, okay, I'll kind of give you the answer. I think there might be a better answer, but I'll give you an answer which is kind of how I got to this, right? So, if you take this anomaly equation, which there maybe you can argue that this thing is, in this kind of more limited context, that this thing is quantized, and you try to write down an action a kind of Goldstone action for this anomaly equation, okay? Kind of pion theory that reproduces this anomaly. Well, you'll get precisely this kinetic term, right? You'll get precisely, it's kind of like a Carol boson. You'll get this kinetic term with coefficient kappa. So in this sense, in that language, it would have been an easier answer. I think there's a kind of updated answer, but in this language,
Can we just pointed to, did it come from the WCW term?
Yeah, the time derivative part. Yeah.
Okay.
So,
no. Okay. Anyways, let's thank Luca again. So